Hello, so today we are going to take a look at the n-queen problem. So the problem says that it's a famous problem where we have a chessboard, an n by n chessboard, and we want to place n queens such that no two queens attack each other. And the goal of this problem specifically is to return all distinct solution to this specific problem. And so what we mean by two queens attacking each other is that basically a queen can attack another one if they are either on the same row, on the same column, or on the same diagonal. And in our solutions that we will return, so that we can return all distinct solution, we are going to represent a queen placement by the letter Q. And if there is no queen at a specific position, we will just represent it by a dot. So, for example, for the 4x4 chessboard, that specific problem has two different solutions. One of them is placing the queen here in the second position in the first row, in the last position in the second row, in the first position in the third row, and in the third position in the last row. So this is one of the solutions. And so we will need to return a solution represented in this format, and the second solution is here. And we should return only distinct solution. We shouldn't have repeated solution. Okay, so, and if you look at the solutions we have here, no two queens attack each other. Like for this one, this row has only that queen. This column has only that queen, this row has only that queen, and the same thing for the diagonals, both the positive diagonal like this, going like this, and the negative diagonal going on the other direction. Yeah, so this is the problem that we are trying to solve. Let's take a look at how we can solve it. Okay, so let's see how we can solve this problem. So I have here a representation of a 4x4 chessboard. And let's take a look. So one thing that will give away like how we can solve this problem is that the problem asks us to return all distinct solutions, right? And this is kind of an enumeration problem, right? And there is nothing specifically that can, like, no rule specifically that can magically gives us the solution. We kind of have to try and see what works, right? So when we have a situation like this where we have, what we are looking for is to find all solutions, of course distinct here, so enumerating the solutions, and there is no clear rule that will allow us to take a shortcut and find them, we should directly think about using backtracking. And what backtracking means here is that we will just place a queen. Let's say, for example, start off by placing a queen here and saying, okay, where can I place the next queen so that it doesn't attack this one? Let me maybe put the coordinates here. So 2, 3, 0, 1, 2, 3. So if I place the queen there, then I can't place it on the first row anymore, neither on the first column, neither on this diagonal here. So I can't put it here, right? And so what's left here is that, well, I could put it here. I could put it in this position, and then if I now, sorry, this is, can I put it in this position first, like in the second column? Let's try to put it in the second row. So basically, we have the choice here. We could either start putting in the first row or start putting the second column and the first column and then the second column. I will go row by row instead. So there are different ways to solve this. Either start by trying on each row or start by trying on each column. Let me first try on each row. Right? So I place it on the first row. Let me see what position I can place it in the second row, right? So if I try to place it in the second row, well, I can't place it here. I can't place it here either, but I can place it here, right? Because it doesn't conflict with the diagonal, and it doesn't conflict either with the with the row or column, right? Let me just draw this a little bit better. And so this means that we can place it here. Now let's try to place it with without conflict on the third row. So I can't place it here because that would be the same column. Can I place it here? No, because that would be on the same diagonal as this second queue here. Can I place it here? No, that would be the same column. Can I place it here? No, that would be the same diagonal. Okay, so I can't place it in the third row at all. There is no position that works. So I backtrack. So I go back to my previous choice. I cancel it and try another choice, right? We said already that we can't try all of these, so we don't go back to them. This is what backtracking does. It just picks up from where it's left, since it's just going back in the recursion, right? So let's try here then. So we try here. This is, of course, we are trying in this row. And now once we place it there, we try on the row after that. So can I place it here? No, that's the same column. Can I place it here? Well, it doesn't conflict with anything here, so let's try it. So it's just no specific, like, no thinking, just trying the possible solutions that are safe. So I put it there. Now let's try on the third row. Can I put it here? No, that's the same diagonal. Can I here? No, that's the same column. Can I do it here? No, that's the same diagonal. Can I here? No, that's the same column. So this solution doesn't work. So we backtrack again and go back to the row before that. Now the only solution left is put it here, because we tried all the other ones. We can't here because that's the same column. And so we backtrack again and we go back. Oops. So we backtrack again and go back to this row. But this row we already tried all possible positions also. So we go back again and we backtrack and we try the second. So we try the second one, because the row we are just exploring the row column by column. Let's take note of that. So explore row column by column. So that would be just, in our algorithm, it would be just a for loop from 0 to n, right? And so we tried the column there. Okay, so we decided on a position for that row. Let's advance to the next row. So every time we advance to the next row, so in our recursive calls, that would mean row +1 each time. And can we put it here? No, that's the same column. Can we here? Sorry, this is the same diagonal. Here, no, that's the same column. Here, no, that's the same diagonal. So the only position we have left is this one. So we tried there. Then we go to the next row. I think by now you should get the idea of what we are doing here, but let's just follow up until we find a solution, at least one. Now in this row, can we here? Yes, we can. So let's try it, because it doesn't conflict with anything. And so we go to the row after that. Can we here? No, that's the same column. Here, no, that's the same diagonal. Can we here? Yes, we can. So we put it there. And now that's it. We have a solution. Once we reach the last row and we find a position to put the queen without conflicting with another one, we would have found a solution. So here, solution, done. Okay, so now we know how we can solve it by just doing brute forcing every time, going row by row, and for each row trying each possible position, and then once we choose that position, try the next row. If we can't find a good placement for the queen, then we backtrack. So that's what we are doing here. Okay, so how can we represent this? So for backtracking, to the main operation that we are doing here, apart from just recursing, is checking if a queen is safe, right? Queen placement is safe. How can we do that? So basically, a queen can attack another one if it's in the same row or the same column or the same diagonal. So what we are looking for here is a placement such that at column R, so when we are exploring a specific column R, we want a placement, sorry, a specific row R, a specific placement at row R in some column, maybe let's call it I. So row I in column J, we want to, okay, let's instead do R and C. So this would mean that we already placed R-1 rows, or R-1 queens, right? If it's the first row, then we haven't placed any queen yet. But let's just ignore the first row here. This is just what allows us to reason about the other rows. So a placement here is safe if, so it's if same row, not same row, right? So not same row as R-1 queens, and then not on the same column as R-1 queens, and not same diagonal. Okay, so how can we, so you can see here, to find if a specific placement is valid, we need to have the positions of R-1 queens, right? So what this would mean here is that we need to keep track, so keep track of placements of R-1 queens, right? And we will need this anyway later on to provide the solution that the problem asks us, because the problem asks us to return like the full board that solves the problem. Like for this case, Q dot 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 Q, and then Q dot dot dot, and then dot dot Q dot. So at the end, we will need to return this. And so to be able to do that, we will need to keep track of all the queen's positions anyway. So we need to keep track of it for two reasons: for this, and to be able to check if a placement is safe. So what this tells us is that we need to have some kind of data structure that keeps tracks of the positions of the previous queens. So IJ, the previous queens, the previously placed queens. So we have the choices. We could use an array, we could use maybe, yeah, anything we want, but one thing that will help us quickly just add to the data structure, where we can quickly add and quickly remove, like when we are backtracking, we find like we put in a position, let's say here, and we find that it's not valid and we want to backtrack, then backtracking means we want to remove that placement from the set, because we are no longer placing the queen in that set, right? So the ideal data structure for that is a set. So this means here that we will use a set, right? Okay, so for our backtracking, the additional data structure that we will use to keep track of the R-1 previously placed queens is a set. Okay, so once we have the set, what does this mean? So we can just, to check if a queen placement at RC is safe, we can just go through the set, check if there is any row that has in the previous placement that has the same row or the same column or the same diagonal, and that's pretty much it. So let's try to write this down. So for backtracking, usually the solution has kind of a template where we could say, so here, let's say solve n queens problem, right? So we get an n, right? Just the length of the n by n chessboard. And in our solution, as we said, we explore row by row, right? So what this would mean is that we need a recursive function, let's call it solve, that will need to be passed a row, because at each time, after each row, we will recurse on this with the next row, so row plus 1. So our initial call here, let's place it here, would be solve, to call it on the initial row, which is row 0, right? But we also said that we would want to pass set here to keep track of the previously placed queens. Our set can be initially empty, right? And so here, for the solve recursive function, we need to pass it the set of queens that we already placed. Cool. Okay, so now what is our base case? When do we know that we are done, that we've finished? Which is usually for backtracking solutions, the base case is when we know that a solution that we were constructing is a solution to the problem overall, right? And so in our case here, we are done when we reach the last row and we do a placement there. And so when we reach the last row is n-1, and so then when we have found the solution to n-1 solution, we would have increased row to row plus 1 because we found a solution, so it would be n, right? So this would mean if row is equal to n, that means we already found the solution for the last row, and so we are done. So here, this means that queens, we have a solution basically. So we have a solution. Okay, so here, let's just put a placeholder here. We could write the method later to construct the solution. Construct solution. We would just take the queen set and create the board that looks like this from that queen set, right? And once we do that, we can just add it to the self.res. So maybe and add it. So this would be our final result that contains all the solutions. So we'll need to define it here before calling the function. Let me just put this down a little bit so that we can have some space. And we need to start solving from 0 with an empty set. And at the end, we should return all the solutions that we have put in this result array. This is in Python, of course. Now, if it's not a solution, so here we should return also. So let's just return because we are done exploring here. Okay, so now the next step is basically when we are exploring a row, we go column by column, right? That's what we said here, right? So when we are trying to explore here, we tried here and then we went to the next row. So to do that, we can just do a for loop here for j and try all the possible columns, which is just trying a range of n, right? And then at each step, what we did is once we chose a column, which it would be once we are in an iteration of this for loop, we try to check if a placement at this j, for example, is safe or not, right? So to do that, let's just have a subroutine that checks if it's safe. We will write this later. And we pass to it the coordinates, which is the position, the row position is row, the column position is j, and we pass the positions of the previous queens because that's what we will be using to find if there is a collision or not, like if another queen can attack the queen at row and j, right? So we'll pass the queens here. And if it is safe, that means we can proceed. And so in like backtracking template or backtracking way of doing things, this is called constructing the candidates, right? The possible candidates for solution, right? So at the next row, all the candidates that we have are all the position in the column, right? So we tried all of them. And now we can, once we choose a candidate, we will need to make a move, right? Or make a choice. And then recurse using that choice. So making a choice here means placing the queen at that position. And in our solution here, placing a queen at a specific position means just adding the queen to adding the position to the set of queens. So that would mean the position is row j. So we add it as a pair here, right? Now we need to recurse. So we do that. So recurse on this with this solution here, which means, okay, we chose a placement at this row. Let's go to the next row. So to go to the next row, we'll just call the function again, solve, with row plus 1. And with this set where we added this queen's placement, right? And then once we explored that, once we exit the solve function here, that means either we found a solution and we will need to try to find another solution, or we didn't find a solution and because we didn't find any safe placement. And then at that point, as we did when we were doing it by hand, we went back to the previous row, right? So going back means just let's remove this choice because we are no longer considering that placement. So we can just, since this is a set, we can just remove the placement row J, right? And that would be pretty much it for the template here. The only remaining things would be to create the two functions isSave and the one that constructs the solution, right? So yeah, those are pretty much the two things that we need to do. So let's write them down. Okay, since I no longer have space here, let me just write these functions maybe here. Yep, let's write them here. So the first one we need is safe here. So let's define it. So if is safe, we get the positions. Let's call them R and C, and we get the queens, the already placed queens, right? So we can just go through each position of the queens and check if they attack this position, if any of them attacks this position. So to do that, we can just go through them. So we can just say for IJ in queens, so we check for every previously placed queen position, and we know that it attacks it if it's in the same row. So let's check if it's in the same row. So if that means the same row means I equal to R, or the same column, which means G equal to C, or the same diagonal. Now the same diagonal is a little bit more complicated. One rule that is good to know is that if we have a diagonal like this, they will 2 points. So for a same matrix like this point and this point are in the same diagonal because the difference between this is the same as the difference. The difference here between them is the same as the difference on the y axis. If we take a little bit more, so this one and this one are on the same diagonal because the difference between their x coordinates, which is here, is the same as the difference between their y coordinate. And the same thing in the other direction. If we take a point here and a point here, they are on the same diagonal because the difference between their x's is the same as the difference between their y. And like in terms, mathematically speaking, if we want to formulate this in more mathematical terms, is that the slope of 2 points on the same diagonal is either 1 or -1. It's -1 if the diagonal is in this it has a positive slope. So it's -1 if it's this way. It's -1. If it's a diagonal in this direction instead, the slope would be 1. And so all we need to do is check that the slope is either 1 or -1, which means that all we need to check is the difference, the absolute difference between, if we have two coordinates, let's say x1 and x2 and y1 and x2 and y2. If we want to know if they are in the same diagonal, we can just check the absolute difference between x1, between the x's coordinates, is equal to the absolute difference between the y coordinates. Why does this matches the slope being 1 or -1? Because the slope is just x minus, the absolute, it's just x -1 minus x2, x1 minus x2 divided by, or is it the reverse? Yep, it's the reverse. So it's actually y1 minus y2 divided by x1 minus x2. So this is the slope, right? So this we know for the diagonal, if 2 points are on the same diagonal, it's either minus 1 or 1. So if we just kind of try to put this on the other side and this on the other side, we can just say that we have either x minus x2 is equal to minus y2. This is if the slope is minus 1, or it's equal to y minus y2. So to do these two here, we could just group them in one condition, right? And just check if the absolute difference between x1 minus x2 is equal to the absolute difference between y1 and y2. And that will pretty much check if they are on the same diagonal, either on this direction or the other direction, right? So that means here that what we need to check is or the difference between the x coordinates, which is r minus I, and of course we need to take the absolute values. So the absolute difference between r minus I is equal to the absolute difference between c and j, right? So if any of these condition is true, they are either on the same row, same column, or same diagonal, then we should return false because it's not safe to place the queen there. Otherwise, if we don't find any queen that can attack this placement, then we can return true. It is safe to place it there. Okay, so now we finished with our check for is safe function. The only thing remaining to do here is to construct the board out of the queen set, right? So to do that, let's just create a function here, call it build board. And that function, we will pass the set of queens placements, right? We call it once we place it all the queens. And so let's just create a board with only dots, right? With only dots. So that would mean, so we want n dots and then n rows. N dots on each row and then n rows. So let's say n range n. And this is for range of n. Okay, so now we have the board without the queens, so it's just all that. So now we want to place the queens, and represent them with just q, so that we can get this representation here, right? So to do that, let's just go through the positions of the queens. So that would mean for RC in queens, this is the positions. All we need to do is just assign q to that position, right? So just say this is equal to q. And then at the end we can return the board, except there is one thing here. With creating the dots this way, we will have something like this, right? And maybe if we place the queen, it would be like this. But the solution, what we want is dot, 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 q. So we want it to be one string. So we can just convert it here to make it one string. To do that, we can just use join a row for row is in board, and we can return that. And this will return it in the format that we want here, this format here. Okay, so now that we know how to construct the board from the set of queens, let's use that function here. So to use it, we need to just say solve.res. We want to add to the overall list of solutions, we want to add the board that we are building. So we build the board using the set of queens and we add it to the solutions. And so this is, instead of add, it's append, since res is a list. So let's say append. And that's pretty much it for the solution. So let's just reiterate again what we did here. So we are using backtracking. We do the base case where we check if we have a solution, which we have it when we reach the final row, and we place a queen in the final row. And then for each row, we try each column. and for each column, we check if the position at that row in that column is safe, using the previous queen's placements. And we make a choice by assigning a position to a queen and adding it to the set of queen's placements. And then we recurse by trying on the next row. If it doesn't pan out, or we found a solution and we added it and we want to look for another solution, then we need to backtrack from this position, so we remove it from the queen's set. And we keep doing this until we are done, which is here when we reach the final position, when we have placed the queens in the final position. And then at the end, we just return the list of solutions that we constructed here. And for checking if a queen is safe, we just check that it's not on the same row, same column, and same diagonal as any other queen. And that's pretty much it for this solution. Okay, so let's type this solution and just run it on a couple of examples and make sure it passes correctly. Okay, so I wrote down the solution that we just went through in the overview here. So we have our main solve function, where we start out with just an empty list that we will put the solutions in. We call recursively our solve function with the set of queens empty initially, and then we start recursing. So we have our base case here. When we have a solution, we process it by building the board and adding it to the list of solutions. And here we start our backtracking procedure, which is try for each row, try every column, and then for each column, check if it's safe to place it there. If it is, make the move by adding the queen to that position, recurse on the next row, and then once we are done, either we found a solution or we didn't find any safe position in the row, then we need to go back. And so to go back, we remove the position from the set of queens, and that's pretty much it. The other thing to check is if it's safe. We just go through the previous queen's placement and check that it's not in the same row, again same column and same diagonal. If we find any occurrence, that means another queen can attack it, so we return false. Otherwise, if we didn't find any, we return true. And then here, the other thing is we building the board when we find a solution, which is just initialize the board with just dots, check for each position of the queen, add Q, and then just return that in the format that we want. And I have it here, some examples to run it on n by n chessboards with n from 0 to 6. So I'll just sanity check the solutions here. So you can see for 0 empty board, there is no solution. For a board 1 by 1, there is one solution, which is just placing one Q, one queen basically. For 2 and 3, we don't have any solutions. For 4, the example that we had, you can see here we have the same solutions that we said in the description. These two here. For 4, we have also the working solution. I spot checked them, and they look good in terms of that no queen attacked another one, and the same thing for 6. Okay, so that's pretty much it for this solution. We can probably make it a little bit better. For example, here we could use any instead of and just check for any occurrence of these. But overall, this is a very good example of how to use backtracking to solve a problem. Yeah. Yeah, so that's it for this problem. Thanks for watching, and see you on the next one. Bye.